So hello, welcome student to this lecture, and this is course number MA412 Linear Algebra, and this is lecture number 33. Okay, so today we will discuss about spectral decomposition theorem for normal and self-adjoint operators. Okay, this is more general for inner product space. I think we have discussed similar results for diagonalizable operators. Okay, and almost similar kind of results are true for normal and self-adjoint operators. We'll discuss that. Okay. So before we discussing self-adjoint operators, normal operators and their spectral decomposition, so let us recall what was projection. So projections. Okay. So if you have a vector space which you can write down, say direct sum of two subspaces W1 W2. Okay. And then if you define a map, okay, so what does that mean? That means any vector can be written as v1 plus v2 of this form. And then you define a map from V to W1 such that P of V is going to V1. Okay, then this kind of maps are called projection on W1 along W2, right? So the problem of this kind of projection was that these kind of projections are not actually uniquely determined by the range. What does that mean? That means suppose you have say V is W1 plus direction W2 and also say W1 direction W3. This does not imply that W2 and W3 are equal. Okay. For example, suppose in R2, suppose we have this, which is generated by say vector 1 1. So here W1 is also generated by vector 1 1, and you choose a W2 something here and W3 something say here. Whatever. Okay, so this is W1, W2 and W3. Okay, now we check if W3, if we choose say W2 is generated by something say 1 2. Okay, substitute generated by 1 2, and W3 something substitute generated by 1 say 5 something, whatever. Then you can easily see that V, which is R2, right, which is exactly direct sum of W1 plus W2, is also W1 plus W3, but W2 is not equal to W3. Okay, so this kind of projections, the problem is that this W2 W3 may not be equal, right? But now we have learned one thing called orthogonal projections, and orthogonal projection has this property. Actually, orthogonal projection actually does define on by the range actually. Okay, so for projection, what you learned? So we learned that for projections operators, so this kind of t square will be t, right? If t is a projection operator, then t square equal to t. So with the help of these, actually we can actually define. For example, we can write down my W1 is what? W1 is in the case of that map T going to this map. Okay, so my W1 is kind of range of V, right? So I obviously I can write down actually is kind of V to V also by this map. Then W1 will be sitting inside V, and it will be in the range of V, right? So you can write down W1 is that range of that operator T which is actually collection of all t x belongs to v, whatever. Yeah, okay. And you see the what is W2. So in W2, whatever the elements are there, W2, they are actually belongs to the null space of that thing, right? Because any element of W2, if you choose an element, say x belongs to W2, then what is the representation of x? So x can be written as 0 plus x, where 0 belongs to W1 and x belongs to W2. So hence t of x will be 0 because it maps to the first coordinate, right? So this is kind of null space, and this is the range of this, right? Okay, so so with the help and that also implies obviously t square equal to t for any projections. Okay, so this is for any projections. Okay. Now you remember in the method of least square method, and also before that we use something called orthogonal projections, and here we will define what is an orthogonal projections. Okay, properly. Okay, so orthogonal projection. Okay, so what is that? So suppose you have a inner product space, say let V be an inner product space, and you choose T from say V to V be a projection. So a projection means T square equal to T, that is given to you. Okay, so so this is any projection, it can be anything. Now when it's called orthogonal projection, so we say T is an orthogonal projection if something more happened. So what is that? So this range of T, you take the orthogonal complement, that there has to be the null space of T, and vice versa. Null space of T part will be the range of T. Okay, and this is I did not assume that T is finite dimensional or not anything. Okay, so in this case, for example, in this case, that in the first previous example, this W1 is actually orthogonal complement of W2, and W2 is orthogonal W2 if T is a orthogonal projections. Otherwise, it's not true actually. Okay. Now in the case when V is finite dimensional, then you don't need both the conditions. So this condition 1, condition 2, you don't need this, one implies another for finite dimensional. Okay, so if this dimension of V is finite, then what happens? Then you see that only one condition is enough. Why? Because if we assume that range of T perp equal to null space of T, and then you know that for finite dimensional case, for the case of finite dimensional inner product space, range of T double perp means you take orthogonal complement, and then again it will be the full the original range of T. This is a very simple exercise. You can do it for finite dimensional case. Obviously, it's not true for infinite dimensional vector space. Okay, inner product space. Now on the other hand, this is nothing but null space of T. Okay, and this is obviously the second condition. This condition. Okay. So for the case of finite dimensional vector space, you can assume you can prove any of the condition. The other will be obvious. Okay, and so this actually help us to define projection, orthogonal projection with the only one condition for finite dimension inner product space. So now then okay, so now suppose suppose you are in a finite dimensional space, and you want to know whether orthogonal projections uniquely defined by the range or the range of the operator or not, then you can see that this is actually defined by that. So what does that mean? That means suppose you have two orthogonal projection on so you start with that. So this W is a subspace of V, and the dimension of W is finite. Okay, and you suppose T1 and T2 be two orthogonal projections. Projection of V onto or on whatever W. Then what happened? Then actually this you can determine this, because then you can say that T and T1 are equal. Why? Because you know the range of T1 will be equal to W, and which is equal to range of T2 also, because this is projection on W, right? And once you know the range, then what is the null space? So null space of T1 would be equal to range of T1 par, but range of T1 and range of T2 equal, so that will be range of T2 par. But T2 is also orthogonal projection, so it will be null space of T1, T2. Okay, so null space are same. Okay, so so done. So why? Because for any projections T, so you originally in a plus, but you can write down actually range of T plus null space of T, right? This is for any projection, right? For any projections. Okay, and hence these T1 and T2 are equal because they have the same range and same null space. Okay, so this implies T1 equal to T2. And so you understood that what is the significance of orthogonal projection. It is not true in general for any other projections. Okay, for orthogonal projection it is true, and not only that, if you choose a infinite vector space, still they may not be true, because infinite vector space you may have these conditions may not be true, that null space of T1 is range of T1 star. Okay, in general. Okay, so what does that mean? That means for orthogonal projection are actually determined by the range itself. Okay, so that's why it is different from the actual projection, like ordinary projection what we have discussed earlier. Okay, so now let us come to the some of the properties of orthogonal projections, and in the case of inner product space, and then we will have this following theorem. So this theorem tells us that what is the classic, what is the equivalent forms of orthogonal projection in a product space. Okay, so you start with a linear operator on a finite vector in a product space. No, I don't need finite dimension. I think you can do it for anything. So let T belongs to LV, and V is in a product space. Okay, and V and in a product space. It can be finite, infinite, anything. I don't care. So then we say that it's orthogonal projection. So then T is orthogonal projection if and only what happened? You can only that adjoint of T actually exists, and not only that, it is actually T self adjoint. So what does that mean? You can only T star exists first of all, and T is self adjoint. What does that mean? And so obviously for projection, you know that T square equal to T, but in this case T equal to T star also. So projections, orthogonal projections are actually self adjoint operator. Okay, so this may not be true in general for any ordinary projection. Okay, but for orthogonal projection they are self adjoint. Okay. So how do you prove this? The proof. So you start with the fact that T says so given that what, so T, so you prove both the case. So first you prove that these orthogonal projections and assume that, and then you prove that adjoint exists. So so it is orthogonal projection, right? So that means what? That means T square equal to T. That is obvious because projections have this property. So now I need to prove that T star exists and T equal to T star. Okay, but because T square equal to T and T is a projection, then we know that you can write down V equal to range of T direct sum of this null space of T. That is obvious that for every projection you can do this. Okay, and also is because it is projection, is given orthogonal projections. So we know that range of T, you take this perpendicular, that orthogonal complement, that has to be null space, and other way also. Okay, and obviously null space. This is given to you. Now with this, all the help, how do you prove that T star exists, the adjoint exists? So so you start with two vectors, any vectors. So you check any vector, say U and V belongs to V. Then you write down U equal to say U1 plus U2, where and V equal to say V1 plus V2, where this U1 and V1 are element of the range. So where U1 V1 belongs to range of T, and U2 V2 is the null space of T. Okay, suppose this is given to you and you have this, then what will be then how do calculate this inner product? So T of x, T of U comma V, what is this inner product? So by definition, this is actually, you write it down as, okay, first of all, because T is a projection, I assume that, okay, here orthogonal projections, so I know that T of U equal to U1, T of V equal to V1, right? So here T of U equal to U1 and T of V equal to V1. Given to us. So T of equal to U1, so you can write down this is U1 and then V1 plus V2. But that you can write down U1 inner product with V1 plus U1 inner product with V2. Okay. Now you see U1 and U2 as U1 and V2 are actually on the different subspaces, right? U1 is inside that range of T1 and V2 is the null space of T2, but they are all null space of T and range of T are orthogonal. So this goes to 0. This vanishes actually, right? Because as, so this is as U1 belongs to range of T and V2 belongs to null space of T, which is nothing but range of T bar. Okay, so they vanish this inner product. Okay, so you have U1 equal to V1. Now U1 equal to V1, this is one way obviously. On the other hand, you prove the value. Okay, so this is I assume U and B for arbitrary for any. So these are arbitrary U and B. Okay, so for arbitrary U and B, you compute T U comma V is of this form. Similarly, you compute that U comma T V, and then you will see that so you can be written as U1 plus U2, but TV equal to V1 because it's projection the first component, right? And hence again you can write down as U1 inner product with V1 plus U2 inner product with V1. And the similar argument tells you that this is 0 because U2 in the null space of T and V1 in the range of T, and they are orthogonal, so this is 0. So you will have U1 or V1. Now you see this is exactly equal to whatever we have find out here. So this is U1 V1, right? This is exactly equal to TU V, right? And so this is true for every UV. For every UV belongs to V. Okay, so you choose any vector, and you see that UV is nothing but U comma TV. So what does that mean? That means T star exists, and that is nothing but, so this implies that T star equal to T itself, right? T star exists and that is equal to T. So this is the proof. So you can find out existence of adjoint where you have T orthogonal projections. Okay. So what does that mean? That means doesn't matter the vectors, the inner product space finite or infinite dimensional. Whenever you have projection map, the adjoint operator always exists, and that it has to be self-adjoint also. Okay. So this is one part is obvious, so we just prove it. Now converse part you need to prove. So this is if and only condition. So conversely, so we just prove the necessary part. If something has to do orthogonal projections, then the adjoint has to be exist and it has to self adjoint, right? Now the subjacent part we need to prove. So conversely, let T is given such that T square equal to T equal to T star. Okay, that means T star exists and T equal to T star self adjoint. Then we need to prove that the map T is actually orthogonal projection on V. So what does that mean? That we need to prove both the case that range is orthogonal to null space and null space orthogonal to range. Okay, both the case. So we start with the range first. So so let you start, say some vector V belongs to range of T, and then another vector you choose, say U belongs to, say, null space of T, and what you can write down. So because V is range of T, so V can be written as V equal to T of V, because when you choose an element in range, then the projection will be same, right? And you also know that T equal to T star, so you can write down this is T star of V, right? This is obvious. Okay, so when you take inner product with U, then what happens? Then you take V inner product U, and then you see that you can write down this is TV and U, but TV is nothing but T star V, so you can write down that T star V U, and then use the inner product adjoint properties V T of U, but T of U, so U belongs to null space of T, so T of equal to 0, so it is V comma 0, so it is 0. So what does that mean? That means U and V are orthogonal to each other, and hence if you start with V is range of T, and that will tell you that V is orthogonal to U. So what does that mean? That means B is inside the null space of T parp, right? Because U is inside the null space and B is orthogonal to any vector of the null space. So B is actually in the perpendicular subspace of null space. So this implies that B belongs to N of T parp, and hence thus range of T is a subset of whatever, of null space of T parp. It's obvious because I choose U and V are all arbitrary. So for any such V, it has to be inside null space, right? This is one part, is obvious. Now you need to prove the converse part. Converse part means what? That if you choose any vector in null space of T parp, then this also element of range of T. Okay, that we need to prove. Okay, so so again, if you say V belongs to null space of this parp, and what I need to prove? I need to prove that B is also element of range of T. What does that mean? That means, so if this, so our claim is that TV equal to V, right? If I prove TV equal to V, that means V is a range of T, right? That is, V belongs to range of T. This I need to prove. So I need to prove that TV equal to V, and otherwise, so that means that TV minus V, this is a zero vector, right? So let us find out what is the norm, then I will understand that is zero vector or not. So if you start with V minus TV and take norm square, you know that this is inner product with V minus TV, comma V minus TV, but that is nothing but V comma V minus TV minus TV comma V minus TV, the property of inner product. Okay. Now note that this V minus TV is a vector which is in the null space, right? So now note that T of V minus TV is nothing but TV minus T square V, but T square V equal to TV, because T square equal to T, so TV minus TV is equal to 0. So what does that mean? That means this vector is a null space of T. So this is the null space of T. But V is the perpendicular to the null space of T. So that means these two vectors are orthogonal to each other. So this quantity will give 0, right? Because one vector is in the null space, another vector V is the orthogonal perpendicular to null space. So that means that is 0, right? Okay. So if this is 0, then what happens? Then you can write down this is exactly only equal to minus of TV comma V minus TV, right? Okay. So the norm of V minus TV whole square is now minus what was the vector? TV minus, okay. So TV minus V comma V minus TV. Clear? Okay, so now I will use that fact that the property of adjoint. So this is write down V minus T star of V minus sorry, so let me write down together V minus TV, but it is given that T star equal to T, so again you can write it down. This is TV, so you can write down TV, and T star equal to T, so this is T into T square, but T square equal to T also. This is TV, so what does that mean? That is 0, so this is V with the 0 vector, and inner product has to be 0. So the norm of T minus V, this is 0, and so this implies the norm of V minus TV has to be 0, and this implies that TV has to be V, and hence V is in the range of T. Okay. So what we prove? We prove that if you start with something which is in the orthogonal complement of null space, there has to be in the range. So what does that mean? That means finally we had range of T is nothing but null space of T hat. Okay, so one part is obvious, so you just prove it. Now another part we need to prove. So we need to prove that range of T par is also null space of T, right? That we need to prove. Okay, so now, okay, so next is what? So next we need to prove. We need to prove that range of P par equal to null space of T. That we need to prove. Okay. Okay, so we already proved that range of T is actually nothing but null space of T perpendicular. Hence, range of T par will be equal to null space of T double par, right? This we know. But for fundamental case, the theorem is done because that is has to be equal to null space of T. But in general, for infinitesimal phase, this is not true. So what is true? This is always true. The null space of any linear operator is actually inside double part of the null space of T. Why? Because the moment you choose any vector which is inside null space of T, and that will be, so this is because this is as for any V belongs to null space of T and U belongs to null space of T par, you know that inner product of U and V is 0, right? So what does that mean? So U is orthogonal to V and V is orthogonal to U. So if V is orthogonal to U, then this also, so this implies V is actually inside part of U, but U is inside here, right? So is inside null space of this part. So if you start with anything from null space of T, it has to be inside null space of T double part. So one part is obvious, right? So the only thing we need to prove that the other part is also obvious. That then we are done. Okay. So so what does that mean? So we just prove that null space of T is sitting inside. So null space of T is sitting inside range of T par. Okay. Now we need to prove the opposite one, that if you start with something in range of T par, there has to be inside null space of T. Then we are done. So now you choose something. Okay, so let something say V is inside the range of T par. Yeah, this is given to us. Yeah, and I show that this is null space of T. So something in null space of T means what? That means T of V has to be 0. So now our claim is that this belongs to null space of T, that is T of V has to be 0, right? This is our claim. So TV, the vector, is a 0 vector. So some vector is 0 vector means what? So there are many ways to prove that the vector is 0 vector or not. The one such thing is that you take the inner product of this vector with any other vector, and so that this is 0, then you are done. So that we will do. So let you choose any, say U belongs to V for any V, any vector inside the vector inner product of V. Then you do the inner product TV of U, and you know that this has to be nothing but V and T star of U, but T star equal to T. So you can write down that this is V comma T of U. Okay. So now you see that TU is in the null space range of T, and V is the orthogonal complement of range of T. So these two are orthogonal, so that has to be 0. Okay. So this is as TU is belongs to range of T, and V is the orthogonal perpendicular to range of T, and this is true for any. So this is for all U belongs to V. So what does that mean? That means TV, the vector TV actually makes every vector 0, and thus means this has to be 0 vector, right? So that means V belongs to the null space of T, and then done. So that finally we will prove that range of T par is nothing but null space of T. And so both the condition is true. Range of T null space of T par, and range of T par is also null space of T, and thus what we prove? We prove that they are actually these two vectors are actually orthogonal and these T's has to actually orthogonal projections. Okay, right? So this is the proof. Okay. Now with the help of this theorem, we will prove our final results, what we call the spectral theorem. Okay, we will prove that thing. But maybe before that, let me give some of the examples and discussion, and we'll prove this spectral decomposition theorem maybe in our next lectures. Okay, so what we'll do, we'll try to understand with some example. So suppose we have something, say, okay. So example. So suppose we have something, say, my inner product space is R2 with standard inner product with the with the standard inner product. Okay, so R2 over R, and we take the standard inner product, and then you choose okay, so we choose my things, say span by 1 okay, so now suppose you have a orthogonal projection, say T is a orthogonal projection from V to V is an orthogonal projection on W. Okay, so if this thing happen, then what happen? Then what will be the okay, so maybe I need one more thing. So the orthogonal projection on W, and then I just want to know that how this T look like, the matrix of T look like with respect to a standard order basis. Okay, and okay, so before that, let me just okay, so let me just discuss one more discussion. So I will come to this. I just want to discuss one more thing. So for find out vector space, what happens? So if dimension of V is finite, and we have W, which is subspace of W, V, which is obviously finite dimensional, then you can choose a orthonormal basis. So for example, you choose orthonormal basis, maybe say B1 is an orthonormal basis for W. Okay, and then we extend it for V. Okay, so and such that this beta 1 can be extended and to an orthonormal basis of basis maybe capital B of V. Okay, Then how do you write down the matrix implementation of T with respect to this basis B? So if you write down the matrix of T with respect to the basis B, then what happens? So B has two components. One is B1, which is the basis of the this range of T, right? Because you are taking this ortho the projection on W, right? So T is actually projection on W. On W. So in the complement of W, it vanishes, right? That is the null space. So what does that mean? That means if you write down the matrix, then it will be so whatever the matrix. So you can have this kind of portion where you have the null space. It is 0, so this is 0 0 0 whatever, and this obvious 0 vector. And for range space, it will be having a very nice form. What is the nice form? It has to be this has to be identity matrix. So maybe it's okay. Let me write down dimension here. Suppose the dimension of W equal to say K and dimension of V equal to N. So this N has kind of is K cross submatrix where you have identity K. This is K cross submatrix, and this is a matrix which is N minus K cross N minus K 0 matrix. Okay, 0 matrix. Okay, why this is happening? Because so in projections T square equal to T, right? So what does that mean? That means this annihilating polynomial will be x square minus x, right? So this will be one annihilating polynomial, and hence and this is obviously x into x minus 1, and minimal polynomial will divide this polynomial, right? So what is the minimal polynomial? It has to be x square minus x, because it cannot be x, then this 0 matrix, it cannot be x minus 1, then it will be identity matrix. So minimal polynomial mx will be x into x minus 1. So the roots are only, so the characteristic roots or eigenvalues are 0 and 1, right? They may be repeat, obviously they will repeat. Now on W, because it takes the image of T is inside W, so when you restrict on W, you will have identity operators, all 1 1 1 1, right? It will be 1 1 1 1, the K cross K matrix, and it will act as a kind of 0 operators on the perpendicular of W, right? W part. So that's why this will be the matrix forms. Okay. So now I just the question I just ask you here. So suppose you have R2 and you have these, and then can you just write down the basis with respect to which it has a of this form? The matrix will be of this form. The answer is yes, we can do it. Why? Because so first of all, W, so my V is R2 is given, and W is also spanned by say 1 1. So what will be one orthonormal basis? So obviously this is not orthonormal. See, any vector, singleton vector is orthonormal, but it's not orthonormal because the norm is norm is not 1, right? So you choose orthogonal basis, it's a B1, so this will be of the fact 1 by say root 2, 1 by root 2, 1 by root 2, right? So this will be orthogonal basis, orthonormal basis of W. Okay. So this is orthogonal basis of W. Now can you extend this to orthogonal basis of R2? The answer is yes, and that is Gram-Schmidt method, right? So so Gram-Schmidt method tells you that you can always extend to any basis to orthogonal basis. So you start with these, and so first of all you take this basis to a and this is a linear independent set in R2, so you can extend it to basis. So suppose this basis is 1 by root 2, 1 by root 2, and then you take say 0 1, Obviously this is a basis of R2, but this is not orthonormal. So now you use Ramsey method to make this orthonormal, right? So this is your W1 and W2, and obviously your W1 you can write down V1, and W2 you have to create W2 from V2. So what was that V2? So V2 will be W2 minus inner product of V2. Okay, so let me write down of the form V1 and V2, then it will be easier. So 1 minute. So I write down by the fact that it is in a product of W2 minus V1, and then you will take this norm of V1 square into V1, and W2 is given to me, and V1 equal W1. So I have to take what is in a product of W2 and V1. But in a product of W2 was 0, 1, and V1 I choose W1, which is nothing but this vector, right? So this is 1 by root 2, 1 by root 2, and then V1 is 1 by root 2, 1 by root 2. Oh, sorry, this I don't need first. Let me first calculate the inner product. What is the inner product? This is 0 times this and 1 times this, so 1 by root 2 is the inner product. And and then what's the norm of V1 is 1, so this person minus is 1. So finally what you'll have, so you'll have V2 will be equal to W2, which is 0, 1 minus this, so this is 1 by root 2 into 1 by root 2 into 1 by root 2, 1 by root 2. But 1 by 2, 1 by root 2 is what? 1 by root 2, 1 by root 2 is nothing but so this 2 raised, so 0, 1 minus 1 by 2, 1 by 2, right? Half. Okay, so now this is obvious, then this is minus of half, this is plus of half. Okay, but see, this is not, again, still this is no longer orthonormal. This is orthogonal too. So now you have to make orthonormal, say U2, which is V2 divided by norm of V2. But norm of V2 is what? So norm of V2 is you take the inner product with itself. Okay, if you take inner product with itself, it will be norm of V2 square will be equal to minus half into minus half, so plus 1 by 4, and then is half into half, which is again 1 by 4. So this is half, and hence norm of V2 is nothing but 1 by root 2. Okay, now you have to divide this by 1 by root 2, and if you divide this by 1 by root 2, it will be root 2 times 1 by half, 1 by half, and hence it will be minus 1 by root 2, minus 1 by root 2. Okay, so this will be the orthonormal vectors. So finally, what will be the orthonormal basis of R2? That will be, first one will be 1 by root 2, 1 by root 2, second one will be minus 1 by root 2, minus 1 by root 2, right? Now see, they are orthonormal to each other. Not only that, orthonormal to each other, and they are norm, both the norm as 1, right? They are the norm 1. Now if you write down if you write down the basis with respect to the map T, okay, so T with respect to this basis, that will be of this form 1, 0, 0, 0. Okay, because one dimensional, so it's kind of, this is identity is 1, 1, and then 0, 0, right? So you can always find out the basis with respect to, you can find out the orthogonal basis with respect to the matrix will be of this form. Okay, So now I will stop here, and in our next lecture we will discuss the spectral decomposition theorem and their properties and their many examples. Okay, let's stop here.